if you're given a first order differential equation of this form, where the y prime is solved for, it's real easy to get a graph of what a solution will be. Okay? We've got an expression dealing with just the y and the t on the right side. But we know that the slope of the tangent line, the y prime, is equal to that function's value. So what I'm going to do is I'm going to pick values for t and y and plug into this equation on the right side, and then I'll know what the slope of the tangent line is at that point. Okay, so let's say I've got a graph. I'm going to have my t-axis, which is my independent variable, and then y is the function that I'm looking for the solution. Take all the points here. So I have the point 0, 0, the point 1, 0, the point 2, 0, 3, 0, 0, 1, 0, 2, the point 1, 1, the point 2, 1, the point 3, 1. I can take a bunch of points and just evaluate this function at those points. So let's say t, y, and y prime will be y squared divided by e to the t. Now, first I'm going to look at what if t is, let me look at y equals 0. If y is equal to 0, y prime is always going to be 0. So it doesn't matter what t value I use. So for any given t, if y is 0, that means I'm looking at points on the t-axis, the slope will be 0. Okay, so what I'm going to do is I'm going to look at, if this is the slope, I want to look at what would a line look like that was tangent to the curve at that point. If the slope is 0, that means the horizontal line, the tangent line, will look something like that. Now that's just a little bitty, picture of that tangent line. But what I'm going to do is I'm going to draw that tangent line at this point, t comma 0. Now t can be anything, so t could be 0, t could be 1, t could be 2. So I'm using the point 0, 0, 1, 0, 2, 0, 3, 0, and that would be continue throughout. Likewise, if t was negative, the slope of the tangent line will be 0. Okay, now let's look at t being 0. If t is 0 and y was just some number, then this y prime will be whatever the y value is squared over 1, because we'll have e to the 0. So it's just that y squared. So now let's pick values for y where the t is 0. That means we're looking at points along the y-axis. So if y is 0, of course it's going to end up being 0. If y is 1, this will end up being just 1. If y is 2, this will be 4. If y is 3, this will be 9, and so on. So I'm looking at the points 0, 1, 0, 2, and 0, 3, and these are the slopes of the tangent line at each of those points. So at 0, 1, the slope of the tangent line is 1. Now what does a tangent line look like that has a slope of 1? That means the rise over the run is 1. Okay, so that means if I go up 1 and go over 1, that's a slope of 1. A slope of 4 would mean for every 4 units I go up, I go over 1. So it would be like this. So that's a slope that's 4, and this is a slope that's 1. And you can imagine 9 is for every 9 units you go up, you go over 1. So it's even going to be steeper. So let me draw some of those on my graph now. Slope of 1 at the point 0, 1 would be a line that looks like that. A slope of 4 at 0, 2 would be something like that. And then 9 is almost going to be vertical. Okay? Now let me look at other values. If I'm fixing the y value at 1, and then I'm going to vary what the t values are. This expression, y squared, okay, the y value is 1, so that would be this part's 1. The y squared then, the y prime, would be 1 over e to the t. So now as t gets larger and larger, I'm going to put in t equals 0, and we're at 1, t equal 1, and we're going to be 1 over e, so that's about 1/3. So that means my slope needs to be about 1/3 at the point 1, 1. Now, a line with slope 1/3 means every one it goes up, it's going over 3. So it's not going to be much above a horizontal. It's actually going to, as you go from left to right, these are going to start leveling off. Likewise, at y equal 2. We started with y equal 4 here, but then as the t gets larger, we're dividing by e to the t, so that's going to start kind of tapering off. And so it's going to get to be more horizontal as you go. And that's going to be true across any of those lines. Now, this is a very tedious process. You're picking individual points, t and y, plugging them in to get the slope, and then imagining what that tangent line looks like. What it's doing, though, is it's giving us the flow of this graph. This is called a direction field, or sometimes called a slope field. Each point is representing the slope of a tangent line, and so you can kind of see the general direction that the graph is taking. So you can get a picture of what that function, that y, that solution curve, will look like. Okay. Now this is the direction field for the function that I just had, and you can see that depending on where you put the initial condition, the graph will look different. You know, if I start a point when t is 0, if my y is at 1, it follows that green curve. At t equals 0, when y is, what is that, almost a third, it's almost a horizontal line. So let me look at some more graphs here. Okay, what I'm going to do is I'm going to vary that point. I'm going to change the starting location. So if I put that starting location down at 0, you'll see it never gets off the t-axis. But if I raise it a little bit, those slopes at 0 are rising a little bit so that the graph's, coming up, and it's following the curve. It's following the flow of those little tangent lines. So you see how it's just kind of going up and hitting those little tangent lines almost parallel to them? So that's what you want to do, is you want to try to stay parallel to the little line segments, but it depends on where you're actually starting to see what that initial slope will be. But this is a slope field, and you can vary the initial condition to see which solution curve. So these are pictures of the function y that are determined by that slope that you're given in that differential equation. Okay. So now let's look at another equation. Let's say that I'm given the equation y prime equal 3y minus 6, and I want to graph that direction field. I want to pick certain values. Now I'm going to pick first, where would that slope be 0? Where the slope is 0 is where the tangent lines are 0, and that would mean the function is not rising or falling at all. So first I'm going to check, where is y prime equal to 0? So that's where 3y minus 6 is 0, so that means y would be 2. Okay, so where the y values are 2, which is everywhere along that horizontal line, the slope field, the direction field, would actually have horizontal lines. Those will be the little line segments for the tangent lines. Okay, now if I want to look at the slope, remember slopes and derivatives. When y prime is positive, that meant that the original function y is increasing. So if I'm looking for where the solutions are increasing, the function y, I would want to find where's the slope y prime positive. So 3y minus 6 is greater than 0 when y is bigger than 2. Okay, and likewise, if y prime is less than 0, that's going to occur when y is less than 2. Okay, so it's telling me something about what the function is going to look like, whether it's increasing or decreasing. So now let's see. If we plug in some values, you'll notice here that there's no t on the left side, on the right side of the equation. When there's no t, then I can just plug in y's, and the derivative, the slope, will stay the same for every t value. So that means every horizontal line will have the exact same slope. So let's say we were letting the y values be 0? Well, y prime then is going to be -6. That means everywhere along where y is 0, which is along the t-axis, we're going to have a slope of -6. Now that's a pretty steep decreasing line segment, but it's going to be the same up and down that entire t-axis. Okay, so now let's say we looked at y equal 1. Well, y prime then, by this equation, will be -3. So the slope of the tangent line when the y is 1, now that's everywhere along where y is equal to 1, all the t values. So I'm going to have a -3 for a slope. So now let's try to draw they've got to be the same up and down for every t value. Now, I probably didn't do -6 steep enough. Now, 0, when y is 2, we know that the slope was 0. We already have those drawn. 3, we're going to have +3. That means our slopes need to be +3. So the tangent line slope would look something like that. It'll be the same for any t value along that line. And likewise, when y is 4, we're going to have 6 for that derivative, which is the slope of the tangent line. So it's going to be a pretty steep curve at that point. Okay, so that's our direction field. And we know where based on the initial condition. The initial condition is as long as that curve starts below 2, the function's going to be decreasing. So if we started right here, it's going to be going down and then kind of rising, getting to be steeper and steeper. If it started up above, we see that it is going to be rising, and we see it rises pretty steeply up there. Okay, now it's a very tedious process building that thing, but if you were used to a computer where you could just go through some loops and let t vary, from 0 to 100 or for the y value 0 to 100, you could easily get that slope calculated and put a graph of a little tangent line at those points and get a really nice curve flow there to be able to get an image of what that solution curve looks like. Okay, and what this says is that the computer methods usually approximate solutions by beginning with the initial condition and then advancing the solution in small steps. So they'll just let their h be 0.1 or something and calculate based on different t values there. So they're just going to follow the direction of the field at each time stamp. So just letting that time value increase really small in small increments. Okay, so now this is that logistic equation that we did before. We found the solution for it, and this is a picture of the direction field. I want to look at what would the curve look like with this direction field for these different initial conditions. Now, we'll go ahead and pull up the different pictures. This first one is one that if I had that the initial condition, the number of fruit flies was 25, then that would be the curve. Notice it's going upward, kind of following the same direction that those little tangent lines are following. Now, if I'd started at 0, if there were no fruit flies initially, then you're never going to have any fruit flies. So you don't have to worry about that multiplying. As the number of fruit flies that you start with increases, it will start increasing. Notice the higher initial condition you start with, the faster it's tapering off because it's growing at a much faster rate when you have that many more of them to start with. Okay, so if you started up here at 275, it's going to grow a little, but then it's tapering off at 300, which is that carrying capacity that we calculated. Notice if you started up above 300, because that carrying capacity is 300, it will start declining. So we'll have that the derivative is positive, which means p is increasing. So the number of flies is increasing as long as you start with any number bigger than 0 up to 300, but p prime will be negative, which means that the function p itself, will be decreasing if you started with more than 300 of the fruit flies. Okay, so that's a direction field. It gives us an idea of what the solution curve is going to look like just based on the values of that differential equation because they're giving us the slopes of the tangent lines for whatever value we're plugging in.